Section 5.3, Pathfinding and Traversal. Shortest paths, weighted traversal, and the real-world use cases where graph pathfinding outperforms every alternative. Finding the shortest path between two nodes is one of the most fundamental operations in graph analysis. Neo4j gives you two production-grade algorithms for weighted shortest paths, Dijkstra and A*. The left block shows Dijkstra. You project a city graph with a road relationship type that carries a distance kilometers property. Then you find your source and target nodes by name. Call gds.shortestpath.dijkstra.stream and specify the weight property. The result includes the path itself and the total cost. You use nodes on the path to extract the city names in order. The right block shows A* on the same graph. The difference is the additional latitude and longitude properties. A* uses geographic coordinates as a heuristic to estimate how far each candidate node is from the target. This heuristic lets it skip exploring nodes that are clearly moving in the wrong direction, which makes it significantly faster than Dijkstra on large spatial graphs. When to use which? Dijkstra is the right choice when you have no meaningful heuristic, non-geographic routing, dependency resolution, supply chain networks. It guarantees the optimal path regardless of graph structure. A* is the right choice when you have geographic coordinates or any other good estimate of distance to the target. It can be dramatically faster on large spatial graphs, sometimes exploring only a fraction of the nodes Dijkstra would visit, while still guaranteeing the optimal weighted path. Sometimes you don't want just one shortest path, you want all of them. Or you want the minimum cost spanning tree that connects an entire network. Let me show you both. The left block uses all shortest paths, a built-in cipher function, not a GDS call, to find all paths of equal minimum length between two drug nodes. Below that, a variable length match shows how to find all paths up to 4 hops, ordered by length. This is useful for discovering indirect interaction chains, paths between entities that have no direct connection. The right block shows the minimum spanning tree algorithm. You provide a source node and a weight property, and GDS writes a spanning tree back to the graph as a new relationship type. The spanning tree connects all nodes in the projection with the minimum total edge weight, the cheapest set of roads that still connects every city, or the minimum set of communication links that still keeps a network fully connected. 3 industry use cases. Drug interaction pathways. A drug may not directly interact with another, but both interact with a shared enzyme. All shortest paths reveals those indirect chains, which is exactly how pharmacovigilance systems flag multi-drug regimens for review. Supply chain routing. Dijkstra, on a logistics graph, finds the minimum cost route from supplier to warehouse to distribution center, accounting for transport costs and lead times as edge weights. Fraud network traversal. Money moves through networks of accounts, sometimes through 5 or 6 intermediaries specifically to obscure the trail. All shortest paths between a known source account and a known beneficiary uncovers every viable route, giving investigators the full picture of how funds were moved.